Hello everyone, my name is Pavel, and today I will tell you about parts of the coroutine that considers generators. This is two parts to our session. This is part one, or our one of this session, and actually this is part two of a series of talks that considers coroutines, but you don't have to watch part one in order to watch this session, this part. They are loosely connected to each other, so you can watch part one if you want to, but you don't have to. So we have a number of talks at CppCon 2022 about coroutines specifically, and you could already watched two talks by Andreas Fertig and Andreas Weiss, where they kind of do a bird's eye overview of the coroutines in general. And you are at this currently at this session. And sometime later, Phil Nash will present his take on coroutines while trying to solve his particular problem about dependencies. And the goal of this session is for you to develop intuition about generators, how coroutine generators work in general, how range generators work, including we'll try to grasp how recursive generators work in principle. And I hope we'll have time to see how asynchronous generators work. And disclaimer that code on these slides is not optimal. It is for educational purposes, so you can understand in principle what's going on. But in general, this is not the best way, the most efficient way to implement generators. So let's start. What is a coroutine? A coroutine is a function where you have one of three keywords, starting with co-return, which signifies coroutine return statement, co-await, which corresponds to await expression, and co-yield, which corresponds to yield expression. So if one of these keywords appears in the body of the function, this function is a coroutine. Here's a little taxonomy of routines or program. So you can see that a coroutine is a sibling of subroutine or subprogram. And we have two flavors of coroutines, stackful, which are very similar to what is called fibers, and stackless that we got in C++ 20. We can look back and, as you know, C++ borrowed ideas from such languages as Simula, and Simula, among other things like classes and inheritance, had this, yes, coroutine 60 years ago. Thankfully, we got it now. So the standard says that when the compiler sees a function, a coroutine function which contains a core keyword, it transforms its body as if applying this template that you can see on the right. So loosely, it means this. So we have our function, which is a coroutine. We have, when we call this function, we get to initial suspend point where we can continue execution, or we can suspend the coroutine. Then we execute the body of the function, and then we get to final suspend point. And again, we can continue or rather finish execution of the coroutine, or again, we can suspend the coroutine at final suspend point. I forgot to mention that you can ask questions, and I encourage you to ask questions using the Q&A facility of Zoom. Please, I will try to answer the questions as we go. Now let's see what magic we have to understand and in order to get an idea or mental model or intuition about how coroutines work. We'll uncover just enough. I will try to uncover just enough of that magic so you understand how coroutines in case of generators work, so you can use it on your own. So, the first piece of magic is that core yield expression is transformed into this construction, which is core weight on some promise object on which yield value is called, and expression is passed to that call. We'll not cover core weight, but you can think about core weighting something as some magic that may suspend the coroutine in case the result of that awaitable result, so to speak, is ready, and in case this result is not ready, the coroutine is suspended. So core weight, when you core weight, the coroutine may or may not suspend in general. In our case, it will suspend almost always. The next piece of magic is coreturn, and coreturn is transformed into this construction. We have an expression on its own statement. Then we have return void called on the promise object. In our case, we opt to have void return value, so you can't return any other type. And the optional expression that you can see at the top is optional, so, but it should be of type void. It must be of type void. And finally, after calling return void, we go to final suspend point. So this is executed whenever we have coreturn in our coroutine, or it is executed implicitly when we have no coreturn, but control flows of the body of the function, the coroutine function. So best practices that I have to mention, they loosely consider generators, but nevertheless. So the first part is that asynchronous tasks should be lazy. It solves a lot of problems like concurrent access and whatnot. And that is contrast to eager tasks that start the execution at the moment when you call a coroutine. So having lazy tasks, we can get a result from a notion of that lazy task by core weighting for that result in a coroutine, in which case the coroutine that we core weight in possibly suspends, depending on if the result is ready or not. Or we can get the result of the result that is connected to that lazy object, lazy result, by synchronously waiting. And in this case, the thread that we synchronously wait on can block in case the result is not ready. This is unlike std-future and company, in which case synchronization is always involved, and if you wait on a future, apart from synchronization, again, the thread that is waiting can block until the result is ready. I recommend watching Lewis Baker's talk, Structured Concurrency, Writing Safe Concurrent Code with Coroutines and Algorithms, in which he lays, so to speak, theory behind these best practices. And so let's get to coroutines, to generators finally. Here we have a very simple generator, which is supposed to generate string values as the string values. And inside the body, we have two yields. We yield string literally, and at another instance, we yield a constant, a nested string constant. We can use this generator like this. So we call our generator function. Here, coroutine frame, so-called, is created for us. Coroutine frame contains a promise. A promise is an instance of promise type that we can customize to instruct the backend, the coroutine backend, what to do, when to suspend, when to not suspend, how to yield values, and so on. And apart from the promise type, the coroutine frame contains all other internal needed stuff like state, current state, at which point we suspend it, and local variables and whatnot. So next, after we have done this, we start. Not done yet. I'm sorry. After creating coroutine frame, we start to execute the coroutine body. And in this case, the promise tells us to suspend at initial suspend point. So the coroutine is suspended at this point. And after that, the control gets back to the outside code. So next, we want to get values, to extract values from the generator. So we use a function call operator for that. We call this function call to get a next yielded value. At this point, the coroutine resumes. After resumption, we co-yield the next value, in this case, just hello. After that, the promise type tells us that the coroutine must be suspended, and it is suspended. The control returns back to the outside code, and we get the yielded value. The next call again resumes the coroutine. We execute these statements. We yield the next value. After that, the coroutine again suspends because the promise type tells it to. And after that, we get back the yielded value and can print it to the console. In this example, and in general, f is our generator, and our generator as a variable f is alive until the variable f is destroyed. So the coroutine frame also lives until the generator, the instance of the generator, is destroyed. And of course, in the output, we get hello world. So let's see why we need to suspend at initial suspend point. So in this case, we have a coroutine bar, which gets values, some collection of values, in which case the function getValues may throw. And if in case we get our generator, but do not, for some reason, do not try to extract any values from that, that potential exception is undesirable. So in this case, we just create the generator and do nothing, and immediately after that, we destroy the generator. So we don't want any risks of exceptions. And because of that, following the zero overhead principle, we suspend an initial suspend point, And yeah, as Uncle Ben said once to Peter Parker, what you don't use, you don't have to pay for, according to the overhead principle. And another point I want to emphasize is that you don't have to extract all the values from the generator. So in this case, we created our generator, then we extracted one value. And in this case, the coroutine is suspended after the first co-yield, and we know that it has more values to potentially yield. But at this point, we are done. We can safely destroy the generator and the coroutine and all the resources that it holds. And it is safe to destroy the coroutine in suspended state, in which case all the resources will be freed, as long as inside the coroutine you use something like array II style resource management, so that all the appropriate destructors will be called and will free resources. So I hope you get the idea that you don't have to exhaustively extract all the values from the coroutine in order to destroy it safely. So we have a question. Beginning to coroutines here in the example on the slide 13 or 15. Okay, let's go back. Where would the code suspend in the initial foo call if there were additional code before the first co-yield line? Yes, good question. I need to clarify probably that when we call the coroutine, even if we have any code, any arbitrary code immediately starting at the coroutine body, we still will suspend before executing the body. So if before co-yield, in this case, there is some code, it will not be executed. The coroutine will suspend, in our case, at the initial suspend point before executing anything in the body of the coroutine. I hope I answered it. So let's go back to our slide 15. Yes, so I will reiterate that it is safe to destroy the coroutine in suspended state as long as all the resources are managed in array II style. And of course, you can pass parameters inside the coroutines. In this case, instead of yielding the first value as string literal, we can pass a value, a string value, and we'll see in the output hi world instead of hello world. And everything I said and everything that concerns local variables applies to parameters, because parameters is just local variables which are initialized outside the body of the function. This is the only difference. And another point here I want to make is that since coroutine suspends at one point and returns control outside, it has to store all the information in the coroutine frame. So in this case, this is very similar to lambda captures. And in this case, greeting will be stored in the coroutine frame. So you should, by default, pass parameters by value, not by reference. You should be very careful to pass parameters by reference in case of coroutines, for the reason that they may be stored, the references may be stored inside the coroutine frame to be referenced later, and this creates a headache of lifetime management, and again, by default, you should pass parameters by value inside the coroutines. And otherwise, I will repeat myself, parameters are just like local variables, with the exception that they are initialized outside of the body of the function, and in this case, coroutine function. Okay, let's define our generator type that we use as a result type. And here is an overview of this type, and probably should be no discard, because it kind of doesn't make sense to call a coroutine function to get a generator and then not use it, to just discard it. So probably it should be no discard. And here we have kind of boring stuff, default stuff that makes our type movable and move assignable. And because we defined move constructor, move assignment, we have to define destructor to properly conduct all the operations that we need to conduct in these cases. Then we have our function call operator, with which we get yielded values. Then we have in the private part constructor that accepts a promise object of type promise type that we'll get to in a second. And we have a coroutine handle specialized with the promise type. And this fulfills the purpose of kind of pointer to the coroutine stuff, like coroutine frame and whatnot, and promise that is stored to inside of the coroutine frame. It is very slim. It's usually the size of a pointer, so it's kind of economical to only store coroutine handle in our generator type. And the star of the show is promise type, because the promise type governs basically everything of how coroutine, in this case, generator should behave. And let's start with defining a promise type. So here we have a mandatory set of functions, set of members that we have to define in order to interact with the coroutine backend. These functions are required by the compiler when you want to compile your coroutine code. And here we have a function just for our convenience. It is not mandatory. I defined it for my convenience to use it later in other parts of the implementation. And in private section, we have a variant that signifies kind of the result that we can get from executing the coroutine, our generator. One option is monostate, that is no result. It means that either coroutine yielded no value, or the coroutine is not yet resumed or started. We can have an object of type T, and we can have an exception. So in case we throw an exception inside the coroutine, we store the exception in this variant. So yes, this is the promise type instance of which lives in the coroutine frame. And let's start with our mandatory stuff. So this is get return object, the first function, member function. Its purpose is to return some kind of notion of an object that will be eventually returned from a call to coroutine. So in this case, we just return generator, an instance of the generator. We pass a reference to ourselves, to the promise type, to an instance of this promise type. And it is called when we call a coroutine. In this case, we can define our coroutine foo, and when we call it, this function getReturnObject is called. The backend obtains this object, and this object will eventually end up in our variable f. The next initial suspend and final suspend, they are supposed to return so-called awaitable objects. In our case, we just return suspend always everywhere, as we discussed. And in case of final suspend, we'll discuss it a bit later. Why do we want to suspend always at final suspend point? Actually, I will mention it right now. We want to suspend at final suspend point because all our stuff, our result is inside a promise, and the promise is inside the coroutine frame. And after our coroutine generator is finished, in case it finished the execution, we still want to get the result of that execution. For example, in case of exception, we want to get access to that stored exception. And for that reason, we want to always suspend at final suspend point. And yes, in our example, initial suspend and final suspend tell the backend that we want to suspend at the initial suspend point and final suspend point. The next is yield value. You can see the no except specifications here and elsewhere. I put it here just for completeness. You can plainly ignore it. For example, in this case, we have to specify it in this weird way because not weird way. We'll get to that weird way. But in this case, in case a value of type T can be constructed in a no-throw manner without exceptions, we want to, so to speak, propagate that knowledge and make our function no except as well. And in the body of this function, we just store the result that was given to us. This function is called in cases when we yield values. So remember that co-yield expression is transformed into this expression, into co-await expression, where yield value function is called on the promise object, and expression is passed inside the yield value call. So again, in this case, we return suspend always awaitable from yield value to indicate that we always want this coroutine to suspend at points where we yield values. The next one, the next mandatory function is return void. In our case, we just want to support coroutine statement. For example, if you want to if you want to finish the coroutine early, you can use coreturn. And in this example, we just place coreturn at the end of our function, coroutine function. And let's remember that coroutine expression, coroutine statement is transformed into this construction we call return void in our case on the promise object, and then we go to final suspend. And you don't have to, you can use coreturn at the end, but you don't have to in case you don't use coreturn statement at the end. It will be still called implicitly as if coreturn is implicitly present. So we have another question. If we suspend always on yield value, then do we still need to suspend from our final suspend? Yes, we need to do that. We'll get back to that a little bit later when we have more details. So In 2 words, again, we need to suspend that final suspend point in case we have an exception. And this slide just perfectly comes handy to explain this. When we have an exception, in this case, we have indeed weird no except specification, because the standard doesn't say if exception pointer can be copied non-throwing manner. So we just want to propagate that knowledge. And we just store the current exception in the result. And so when we do this, the coroutine finishes. You can see that in case we have an exception inside our coroutine, we throw an exception, catch it in our body, function body, we catch it in catch clause. We call unhandled exception on the promise type. After that, we immediately get to final suspend, and we want to suspend at that point because we still want to have access to this stored exception. So if we haven't suspended at this final suspend point, the coroutine will self-destruct, so to speak, and we will have no access to that stored exception. We have another big question. So far, I have seen mostly coroutines that are generators of different types. So 2 questions. What is the advantages of coroutine generators compared to the class generator? Implying that all data stored in the coroutine frame could be adequately stored in the class generator. We would need to delete the class object generator equal to destroying the coroutine. So I cannot see practical advantage of coroutine generator. Okay, let me address this point. There is no, so the advantage is that coroutines is basically syntactic sugar. Coroutine function is cut into straightforwardly cut into state machine by the compiler. You don't have to do anything, and you can write your state machine that is supposed to be state machine in kind of a convenient way, using this kind of syntactic sugar, and the compiler will take care about everything like storing intermediate variables that can be needed after resumption, for example. It will take care about optimization. So, for example, you can have a coroutine function body with co-weights and co-yields and whatnot, and the compiler will try to optimize the body. You don't have to do it by hand, for example. And basically, coroutines present another sugary instrument, I'd say, to express what you already can express with other means, like with everything in C++. The second point is, please can you give an example where a coroutine would help with asynchronous I/O from file, network, GPU, etc., involving multiple threads? Thank you. So this second point is out of the scope of this talk, unfortunately, but you can go watch part 1 of this series. Just Google understanding C++ coroutine by example, part 1. And I touch these questions a bit in that talk. Okay, let me refresh what we see in this slide. In case of the exception that can be thrown in the function body, it is caught, and unhandled exception function is called on the promise object. And in our case, we just store this exception as exception pointer that we can later access and, for example, rethrow. Okay, that is all the mandatory function that we need to define. This is the convenience function. Here we just check if we have an exception stored in the result. In case it is we have an exception, we rethrow the exception, and otherwise we just return a reference to the stored value. Precondition to this function is that we must have result to exception. So we should have been should have resumed the coroutine before calling this function. So this is once again the overview of the promise type. Again, this is the type of the promise that lives inside coroutine frame. We get back to our generator type. We define the promise type. Now let's define everything else. This is the kind of boring stuff. We have a move constructor that just moves the value of the coroutine handle from other instance. We have to use exchange because coroutine handle follows kind of pointer semantics. When we move coroutine handle, it is equivalent to copying, so we have to manually set null to the coroutine handle of the other instance. Move assignment is very similar, but before transferring coroutine from the other instance, we have to destroy the current coroutine if we have one. And in the destructor, we check if we have a coroutine that is connected to the with the current coroutine handle. We destroy it as well. So here in the function call operator, we call function call operator on the coroutine handle. This is equivalent to resume function, just a shorthand. In this case, the coroutine is resumed. We expect it to yield values or finish or maybe throw an exception. And after that, after one of those, the control gets back to this code, and we call get value on the promise that we get from the coroutine handle. So the promise called on the coroutine handle gets you a reference to the promise that lives inside the coroutine frame. On that reference to that object, we call our convenience function get value, with which we either throw an exception if we haven't had an exception, or we return a reference to the stored result. So the last part is the private constructor. In this case, we just store the coroutine handle that is connected with the promise. We get the coroutine handle with the from promise static function that is defined inside the coroutine handle that gets for us coroutine handle that we can store in our member variable. And this constructor in our case is used inside the getReturn object, with which we provide an instance of the generator that will be returned eventually from the call to coroutine generator. So again, this is the overview of our generator type. Let's go over our example once again, now with more details. When we call the coroutine generator function, coroutine frame is created for us. After that, getReturn object on the promise object is called, from which we return an instance of the generator that eventually ends up here in the variable f. After that, we start to execute the body of the function, or the transformed body of the function. We get to initial suspend point. The promise tells us to suspend at initial suspend point. We do that. After that, the control returns outside. Next, we want to extract a value from our generator. We call the function call operator. Inside of the function call operator, we resume the coroutine. In this case, the coroutine resumes. We execute all of the statements that we have. In this case, just co-yield expression, which is a statement on its own. When we co-yield something, yield value on the promise object is called. In this case, we just store the result that is given to us in our promise, basically. After that, the awaitable that is returned from yield value tells us that we have to suspend the coroutine. The coroutine suspends. The control gets back outside of coroutine resume. We again call get value on the promise object. Return the reference to that value that we just yielded, and using the get value function where we check if we have an exception, then we throw that exception that was stored, and otherwise we just return a reference to the stored value. In this case, we just return a reference to the stored value. And after that, the control returns outside again, and we can print that value that we got in the console. Next, we again call the function call operator. Everything repeats basically in the same manner. The coroutine resumes. We execute statements. We execute co-yield, yield value. We suspend the coroutine, not at the final suspend point, but at the point after the co-yield. The control gets back to the outside code. We got a reference to the yielded value, and we can print it. And this implementation has two drawbacks. The worst drawback is that we have no means to know if the generator has more values, but this implementation is perfect for infinite sequences. And for example, this is our friend Fibonacci, and this works perfectly with this infinite sequence. So, okay, let me pause. We have a question. How are coroutines better than C++ as the promise and future? It feels like it's quite a bit of work to get it working. So what are the scenarios under which we should use coroutines? So I'd say that the main downside of future and promises is that futures and promises always use synchronization, and in case of coroutines, we don't have to use synchronization in general. So you don't have to pay for synchronization in this case compared to futures and promises. And following the zero overhead principle, using futures in this case will impart an overhead that otherwise you don't need to have. So there are different considerations, but in case of generators, I think they don't concern, other considerations don't concern generators, the case of generators in particular. So I'd say this is the other considerations are outside of the scope of this talk, unfortunately. And again, I will advise you to watch other talks. Maybe again, watch part 1 of this series of talks. And I hope I answered you more or less satisfactory on this question. We have other questions. What will happen when function call operator on generator is called more times than the number of values it produces? Excellent question. This is the next slide. And we have another question. In general, normal users won't need to write generators. Those will come from a library, right? We can just use the provided ones. This is also an excellent point. We have, at least as far as I know, STD generator STD generator specification accepted into C++23. Otherwise, if you want to use something already cooked with the C++20, you can use a variety of libraries like CppCoro or Foley, experimental primitives, and you don't have to, if you really want to, you don't have to write your own implementation. So we have another question. What will happen when function call operator in yes, I already basically in the process of answering this question. So here we can see an illustration. Here, this is the same example. We try to extract values from our generator, but we know that this generator has only can yield only 2 values, and in the code below it works fine 2 times, but in general we don't know what should happen when we call when we try to extract a value one more time. So we will address that in a minute. And another drawback is unnecessary extra copying. So here we see that in our initial implementation, we receive a yielded value by const reference, and we have no choice but to copy the value of that yielded item into our internal storage. And in general, we don't have to do that. So the standard says that when the coroutine is suspended at when we call co-yield and co-wait, or rather when we call co-wait, and because co-yield transforms into co-wait, it applies to co-yield as well. When we call await and the coroutine suspends, all the data that is, in this case, passed into yield value is accessible during the time that the coroutine is suspended. So in this case, we have a constant s. We yield this constant. It is passed to yield value, and the compiler has to ensure that it passes a reference that will be available to an object that will be available during the coroutine suspension. This basically means that this constant should be inside the coroutine frame, so it is saved during the suspension. And here is a more involved example. In this case, we have a string literal. String literal is, for this string literal, temporary object is constructed, then the coroutine is suspended. Then after the resumption of the coroutine, this statement is basically finishes. And this means that only after the resumption, this temporary will be destroyed. So this also means that this temporary should be in the coroutine frame. It also kind of means that if we have a co-yield or co-wait statement as a statement, this statement ends execution after the resumption of the coroutine. So basically, the finishing of this statement tears into two parts. So we execute part of this statement before the suspension, and we finish the execution of this statement after the resumption. So we have more questions. Is there a way that the generator can tell us if the value is ready? Yes, we'll get to that. How can coroutines be used to invoke functions callbacks after an asynchronous operation is run, e.g. invoke callback on receiving response from a service asynchronously? Thanks. Unfortunately, this is also outside of the scope of this talk. We have enough material considering just generators, and unfortunately I can't answer this question in this talk. So, okay, in this case, all of this means that the reference that we get in yield value inside the yield value is valid during the suspension of the coroutine. And at the, actually, at this point, you know almost everything you need to know about how generators work, and the rest is just interface design and making design decisions. And let's see what we have, what we can have. So we can add has value member function to kind of know if the generator has values and if we can try to extract more values. This is the overview of an example of such an implementation. You can see that we have at the bottom a mutable bool. It needs to be there because I wanted to preserve the previous behavior, in which case both trying to extract value and has value has to have to resume the coroutine, and we need to keep that knowledge, that state. And for that reason, because has value is const, we have to make our bool mutable. And well, I think this is ugly. Another option is to have two functions like advance and get value. In this case, the contract is that we have to call advance before we can call get value. If advance returns true, we can call get value, and if advance call returns false, means that the generator has no more values, and we have to back off. So I will quickly run through the implementation here. All the other stuff remains the same. I just made some, in this part, I made some refactoring. Here's the important part. We want to address the unnecessary copying. In this case, we had the previous implementation that copies the value that we get by const reference, and we can add an overload of yield value that receives yielded items by R value reference. And in this case, because the reference stays valid during the suspension of the coroutine, we can just store the address of that variable. And we have to expand our variant, result variant, and add pointer to the resulting value. So this is some refactoring. I just extracted has exception check into its own function. Here I just replaced the check with the call to has exception. This is kind of similar stuff, except yeah, one more point is that now that we have two variants of result, we have to check which type of result we have. If it is just the value, we return reference to that value. If it is a pointer, we get that pointer and dereference it and return a reference to the object that is pointed to by that pointer. I hope it makes sense. And yeah, preconditions as before is that we must have result to exception, and we can write code like this. Here we can use move because we get yielded values by reference, by non-const references. Yeah, but what if we want to only yield values by const references, not just not by non-const references? And you know, overhead, zero overhead principle, and of course we can do that. We can define a specialization of our generator, in which case we have only one overload for yield value, which receives yielded value by const reference. In this case, we store, instead of just copying value, we store a pointer to that value. And consequently, we return a const reference to that value from function getValue. And we don't need to check what kind of result we have at this point. And in the result variant at the bottom of the slide, we don't have to have multiple variants of result, of kinds of results again. And because we defined get value in the generator as a returning autoref, we don't have to change it, but we still have to somehow define a specialization for const T types. So yeah, these are the changes. So we have in our, we get back to non-const ref case, we have two overloads of yield value, one for const values or convertible to const values, one for R value references. So for templates, for example, of moved values, if you use std move. And otherwise, we have minor changes, like has exception is extracted from that. And this is all the changes we need to do in the promise type. We have to define our advance and get value. They are kind of very simple. Inside advance, we resume the coroutine and then check if the coroutine is done, or rather it is not done, or if we have an exception. In that case, we can call get value, and get value just return the reference from our convenient function called on the promise. So, of course, the precondition for the get value function in the generator is that we must call advance in advance. And here how it looks in practice. So here we have to call advance in a while loop in this case. Then if advance returns true, we can call get value. The consequence of that design is that when we have an exception, when we call get value again, we still again get an exception because our generator is kind of in an exceptional state. And okay, we can add has exception member function, which is implemented like this. We just return the result of the check if we have an exception, and we can use it like this. In case we have an exception, we can somehow handle it, and otherwise we can call get value. So this is also ugly, and in fact, the operation that we need is to check if there are values in the generator. We need a means to get a value from the generator, and we need to somehow advance the generator. And all of this is fulfilled by the Iterator interface. And I think we'll stop here because I'm over time, several minutes, and we'll continue from this point in the next slot. So let's have a break. We have no questions, thankfully. Please ask questions in the next part of this session. I will try to answer all the questions, and we'll continue this session after the break. And yeah, see you. See you after the break.